Hello students, today we will explore chemistry, chapter 9, hydrocarbons. So this is our theory part 14 and today we will cover the NCERT section 9.5 in it. This is the disclaimer. Let us start by looking at what we will study in today's lecture. So our focus will be on recognizing and writing the structure of aromatic hydrocarbons. So far, we have seen this term in various discussions, but we have not discussed it in detail. Therefore, our focus will be now on recognizing and writing the structure of this aromatic hydrocarbon. We will also practice drawing this structure and identifying their unique features. After that, we will dive into the structure of benzene and discuss what makes this compound aromatic. Aromaticity is a property that gives this molecule extra stability due to the way electrons are shared in the ring. By the end, you will be able to explain why benzene is so important in both chemistry. Let us talk about the specific names of the NCERT section. Then it is 9.5 Aromatic Hydrocarbon, in which we will see the nomenclature and isomerism in 9.5.1, and in 9.5.2 we will see the structure of benzene. And after covering this lecture, we will do a short summary. So let us begin our discussion on aromatic hydrocarbon. So this is an important class of hydrocarbon with unique properties. We will see that what makes them special compared to other hydrocarbon as we go further. First of all, let us define what is an aromatic hydrocarbon. These are hydrocarbons that are cyclic, meaning their atoms form a ring. They are planar, which means all atoms are present in the same plane and they have delocalized pi electron. So this is the most important part and the stabilizing factor at the same time. Delocalized electrons means they are not fixed between two atoms but are shared across the ring, which gives the molecule extra stability. Now, aromatic hydrocarbons are characterized by a pleasant smell as compared to your alkanes, alkenes and alkynes, which were odorless. It is having a pleasant smell, and hence the name comes from this smell as aromatic. So you must have heard this term aroma. So as a result of this pleasant smell, your aromatic hydrocarbon is named as aromatic, right? Now, this property was one of the first clues that helps chemists identify and group this compound together. Now, this compound are also known as arenes, so Arenes. If you hear the term arene, it means the same thing as aromatic hydrocarbon. It is important to remember both names will be used because you will see them used interchangeably in textbook and exams. Most aromatic compounds contain a benzene ring. The benzene ring is a 6-carbon ring with alternating double and single bond. If you look at the structure, so that is the description of the structure, but not the actual phenomena. But because of the delocalized electrons, so this is the important point, all the bonds are equally lengthed. Okay, this means your structure is a key feature for all the aromatic compounds. So here are some examples. So you can see the structure of benzene. Then we have toluene, in which the benzene ring is along with a methyl group. Then we have naphthalene, which is basically two fused ring of benzene. And then we have biphenyl, where two benzene rings are connected by a single covalent bond. Now, let us focus on benzene. So we'll try to abstract the structure of benzene as much as possible. So benzene is a key example when we study aromatic compound which have unique stability and properties compared to other hydrocarbon. We will look at its discovery, structure and some interesting facts about its behavior. First of all, benzene was isolated by Michael Faraday in 1825. This means Faraday was first to separate and identify benzene as a distinct chemical substance. It is important to recognize how early scientists contributed to our understanding of molecules we now consider as basic. Then the molecular formula is C6H6, indicating a high degree of unsaturation in your compound. Now, let us discuss benzene's stability. Despite being highly unsaturated, benzene is unusually stable compared to other unsaturated hydrocarbon or hydrocarbon with double or triple bond. This stability is a key feature of aromatic compound and sets benzene apart from alkenes, which are generally more reactive. it is capable of forming a triozonoid, indicating the presence of 3 double bond. You can see that when we react in harsh condition, your benzene with 3 moles of ozone, we get triozonide type structure. Okay. Now, benzene has another interesting property, which is it produces only one type of monosubstituted derivative. This shows that all 6 carbon and all 6 hydrogen atoms are identical. Now, this is the most important part. So, if you do the monosubstitution of benzene, you will get the same structure each time, no matter where your substituent is going. This, what does it mean? It means that all hydrogens which are replaced are experiencing or we are experiencing the same chemical environment, and so does your substituent. Now, let us look at how aromatic compounds are classified. Your aromatic compounds are a special group of hydrocarbon known for their stability. So, we have seen this thing so far, and unique ring structure. We will see that they can be divided into two main categories based on whether or they are not containing benzene ring. The first one is benzenoids. These are aromatic compounds that contain a benzene ring in their structure. Benzene ring are again hexagonal rings made up of 6 carbon atoms with alternating double and single bond, which gives them the extra stability. For example, we can have a naphthalene, which is just a fused ring of 2 benzene rings. Then we can have biphenyl, in which 2 phenyls are linked. I would say benzene rings are fused together. Then toluene, which is nothing but a monosubstituent derivative of benzene. Now, let us move on to non-benzenoids. So, these are aromatic compounds that do not contain any benzene ring. Instead, they have other type of highly unsaturated ring that still meet the criteria for aromaticity, such as having delocalized electron and a planar ring structure. Now, non-benzenoid aromatic compound that contain other highly unsaturated rings are azulene, cyclopentadienyl, then we have pentalene and tropene. You have also the structure of one of those, which is azulene structure. Now, moving on further. Next, we will be looking at how benzene derivatives are classified. The main idea is that we group them based on how many substituents are attached to the benzene ring and where those substituents are located. This classification helps us to predict the properties and reactions of this compound. We will break down each type step by step. First one is monosubstituted benzene. It has only one substituent, so it is coming from the name itself. Mono means one. This is the simplest type of substitution, and it is important to recognize because it sets the foundation for understanding more complex cases. Then we have disubstituted benzene, which has two substituents, and finally polysubstituted benzene derivatives that have more than two substituents attached to the ring. Poly means many, so these compounds can get quite complex. The arrangement and type of substituents can greatly affect the chemical behavior of the molecule. Now let us focus on monosubstituted benzene first of all, which is the first derivative of benzene. We will see why all hydrogen in benzene are considered equivalent and what happens when we replace just one of them. This one will help us to understand why only one type of monosubstituted product is possible. So, the benzene ring has 6 equivalent hydrogen atoms. This means that each hydrogen atom is in the same environment. So, replacing any one of them leads to the same product. This symmetry is a key feature for the benzene ring. When we talk about monosubstitution, we mean that only one hydrogen atom on the benzene ring is replaced by another atom or group. This simple change in the basis is the basis for creating a wide variety of benzene derivatives. Replacement of any hydrogen by substituent giving only one type of monosubstituted product. So, example is methyl benzene or toluene. Here we see that we can replace one hydrogen of benzene with methyl group to form toluene. Next, we will study about disubstituted benzene derivative. So, in disubstitution, we replace two hydrogen atoms by monovalent substituents. So, it is very important to remember that we are always replacing hydrogen with a monovalent substituent, because hydrogen is a monovalent one. If you are replacing it, you must satisfy the valency of carbon, that's all. And for that, you have to take that substituent only which is monovalent, means it can form only one covalent bond at max. Now, two monovalent structure can be same or different. So it is not necessary that both substituents, that is your monovalent one, must be different or must be same. They can be same or maybe different. Three isomers are based on the position of the substituent. So this is basically based on the relative position of the two monovalent substituent. The first one is orthoisomer, second one is meta-isomer, and the third one is para-isomer. So starting with the first one, which is orthoisomer. In orthoisomer, the two substituents are attached to adjacent carbon. Specifically, I would say that they are positioned at 1 and 2. So, it is an example of that 1,2-dimethylbenzene or orthoxylene. So, to represent this, we can also write O dash rather than writing it as 1, 2 dash. Continuing with the studying of this disubstituted benzene derivative. Now, we have meta-isomers where the relative position of the two substituents are 1 and 3. So, what we can say, we can write it as M dash rather than writing it as 1, 3 dash. The compound which is given here is known as 1,3-dimethylbenzene, or it has a common name also as M-xylene. Lastly, we have this para substitution. Basically here, the relative position of the two substituents are 1 and 4. Okay, remember, in all this examples that you have seen so far, both monovalent substituents are same. Now, they can be different. You can also take 1 CH3 and 1 chlorine, or you can take 1 NO2 or 1 chlorine. So, all will be considered under this disubstituted benzene. So, here we have an example of same type of substituent, and it is 1,4-dimethylbenzene or para-xylene. Moving on to the third type, which is polysubstituted benzene. So, polysubstitution means you are replacing more than 2 hydrogen atom in a molecule with a different monovalent substituent. Basically, monovalent, as I said, they can form only one bond, same like your hydrogen. This change can significantly alter the molecule's behavior and reactivity. Now, monovalent substituents replacing hydrogen can be same or different. Again, all the substituents can be same or they can be different. For example, we can have 2,4,6 trinitrotoluene, in which all the substituents are nitro, and one of the last one is the methyl. Here, the second example, if you see, we have 5-bromo 2-chlorophenol. Here also, the number of substituents is greater than 2, and all three are different. One is hydroxy, one is chlorine, and one is bromine. The structure shows a benzene ring with several different groups attached, illustrating how multiple substitution can occur. Remember, the position and type of substituents can greatly influence the molecule's stability and reactivity. So, we are done with this type of benzene. Now, we will move on to structure. So, Kekule's contribution to our understanding of this benzene is very specific and very important. Kekule was a scientist who proposed a new way to think about the structure of certain molecules. We will see how his ideas change the way chemists view molecules bonding, especially in ring-shaped compounds which are aromatic. Now, let us see what is his main proposal was. First of all, Kekule suggested that benzene has a cyclic or ring-shaped planar structure. Cyclic means the atoms are arranged in a loop, and planar means all the atoms lie flat in a single plane. This was a big shift from earlier idea which pictured molecule as straight chains. Notice how this ring structure sets the stage for unique bonding pattern. Then after, he also proposed that the bonds in the benzene ring are alternate single and double bond. This means as you go around the ring, you find a single bond, then a double bond, and so on. This alternating pattern helps explain some of benzene's unusual stability and chemical behavior, which couldn't be explained by simple chain structure. So, finally, Kekule's model showed that each carbon atom in the ring is bonded to just one hydrogen atom. If you look at the structure given here, you can see 6 carbon atoms forming a ring, each with a hydrogen attached to it. This structure is key to understand the benzene's property, like its symmetry and stability. Now, we will explore the Kekule's prediction about hydrocarbon, specifically focusing on the isomer of 1,2-dibromobenzene. Remember, an isomer is a compound with the same molecular formula but a different arrangement of atoms. We will see how Kekule's idea led to expectation about the structure and properties of this molecule. Now, he expected that 2 isomers are possible if your benzene is disubstituted. Let's see how. So, these are the 2 isomers. What is the difference between these two? According to Kekule's hypothesis, bromine atom in the first one is added to a singly bonded carbon atom in one isomer. Okay, you can see here that both bromines are across a single bond. Where is the second one? Both bromine are bonded to doubly bonded carbon in the another isomer. Got it? So, in this case, the carbon that you are seeing to which bromines are attached in the second one, both carbons are attached by double bond. In the first one, both carbons were attached by single bond where the bromine was attached. In the second case, both carbons are attached by double bond where the bromine are attached. So basically, Kekule said that okay, this structure that you are seeing, these two structures are two different isomers of your 1,2-dibromobenzene and not a single compound. But if we just move on further, we found some problem with Kekule's structure for benzene. It was seen that only 1,2-dibromobenzene actually exists. There were no two possible isomers. So this tells us that the actual structure of benzene must be some more symmetrical than Kekule proposed. It is an important clue that the bonds in benzene aren't fixed as single or double bond in specific places. So let's focus on the idea of fixed single and double bond here. In reality, benzene does not behave like it has a single fixed bond and a double fixed bond. Instead, all the carbon bond in benzene are of the same length, which means the structure doesn't support fixed bonds as Kekule suggested. This observation changed the original model. Now, Kekule addressed this anomaly by suggesting that the double and triple bond are oscillating and they are oscillating at a rapid speed. Got it? Therefore, we are seeing the same kind of isomer. This means that the electrons are now constantly moving so that the double bonds aren't stuck in one place. This idea was an attempt to explain why all the benzene bonds in benzene are equal. Here you can see a structure showing the shifting of double bond in the benzene ring. Notice how the double bond move around the ring, creating a sort of blurring effect. This helps us to understand Kekule's idea for oscillating bond. But we will see that even this doesn't fully explain benzene property. So basically, he was saying that these two structures were in equilibrium with each other according to Kekule. But it wasn't, I would say, enough to explain the phenomena that were shown by benzene. What were those phenomena? First was unusual stability of benzene. So basically, if I consider a normal ring with alternate double and single bond, it will have a very high energy as compared to the original energy of this benzene. And second one, it shows preference for substitution reaction instead of addition reaction. So you know addition reactions were very specific to double bonded and triple bonded carbon. But here, the idea of this, I would say, prone to this addition reaction was not seen in case of benzene. So now we will see the effect of resonance theory. So it is a concept in which electrons behave in certain molecules. So resonance helps why some molecules like benzene does not fit the simple bonding pattern. First of all, let us start by looking at what resonance means. According to valence bond theory, some molecules seem to have bonds that are constantly shifting or oscillating. This is called resonance, and it helps us explain why we see unusual stability in molecules like benzene. So here you can see a diagram showing Kekule's structure and the resonance hybrid for benzene. These two different ways to draw the double bond and then the hybrid structure with a circle inside the hexagon helps us to understand how the electrons are actually shared across the whole ring, but not just between specific carbon atoms. So basically, this dotted line or this circle is showing that the electrons is not being on one place. Instead of that, it is rotating. Now, your actual benzene structure is represented by a resonance hybrid. So this is just a representation, not the actual structure. It is a representation of your benzene actual structure. And this is the one which we use often. Now this hybrid structure is shown by a circle inside the hexagon. You can see here representing 6 delocalized pi electrons. Means the electrons are not stuck just between two atoms. It is being shared among all 6 carbon atoms, which is adding to the molecular stability. So if you see, then the labeled A and B structure given according to the Kekule were just a kind of, I would say, a representation that was not good enough to explain the actual structure of benzene. Got it? The actual structure is now being represented as hybrid one. So the complete delocalization in this hybrid one is shown by the circle. Got it? So it is not representing any bond or something like that. This circle is just representing that the electrons are being delocalized over 6 carbon atoms. Now, let us move on to the orbital picture of benzene. It is seen that all 6 carbon atoms in benzene are sp2 hybridized. It means one s orbital and 2 p orbitals combined together to form sp2 hybrid orbital. This hybrid orbital lie in a plane which is important for the flat hexagonal shape of benzene. So the image here illustrates the bonding in benzene like system. What you can say here? Though there are two types of bond present, the first is the sigma bond. So sigma bond are the strongest type, as you know, of covalent bond formed by the direct overlap of orbital between atoms. In benzene, this bond creates the framework that holds the molecule together. Now what will happen here? Each carbon atom uses two of its sp2 hybrid orbital with its to form bonds with its neighboring carbon atom. Got it? This overlap forms stronger sigma bond between the carbons, connecting them in a continuous ring and creating a stable hexagonal structure. Now what we will see, that there is a overlap and that is creating sigma bond in the image. You can see the same in the image as well. Next, the third sp2 hybrid orbital of each carbon overlaps with the hydrogen's s orbital. Okay, you can see here that there is one more bond denoted as sigma, and it is the bond with the hydrogen. Now it results in again 6 CH sigma bond. So what are the total number of bond? 1, 2, 3, 4, 5, 6 and plus 6, that is 12. Now let us look at an important point here, which is your 6 p orbital remain in an unhybridized state. You can see here that your p orbitals are represented here. Next, continuing the study of this benzene, we will see on to the formation of pi bonds. So each carbon atom has one unhybridized p orbital perpendicular to the plane of the ring, and this 6p orbital overlaps side by side, and that results in pi bond. This overlap creates a continuous ring of electron density above and below the plane, which is what gives benzene its extra stability. Now, the two possibilities of forming pi bonds are there. The first is that C1 and C2, then C3 and C4, then C5 and C6, they all can pair up to do the sidewise overlap, and this is visualized with the diagram that is given here. Okay, moving on further with the formation of pi bond, there can be a second type of overlapping, which is between the C2 C3, C4 C5 and C6 C1. Okay, so this is the second type of sidewise overlap of two p orbitals of carbon. But what should we take? What should we consider? Which one is the correct one? Now we'll see how this resonance in benzene gives extra stability to benzene. X-ray shows that the equal probability of p orbital of each atom to overlap with p orbital of adjacent carbon atom means it can overlap with either of the carbon present on the both side of the carbon that is present in the benzene ring. Now it is seen that rather than overlapping with the one, there is a continuous overlap between each p orbital of the neighboring part, and that creates a continuous pi electron cloud above and below the ring. So here you can see that all pi bonds are being interacting, and to represent this we have a blue disk which is sandwiched between two electron clouds. So it is basically looking like a sandwich, and the carbon atoms are present in between these electron clouds, and this is represented by your this lobe, this two electron clouds that you are seeing, which are looking like a bun. It is representing the delocalization of pi electron. Okay, so these are two donut shaped electron clouds. One is above the plane of the hexagonal ring and one is below the plane of the hexagonal ring. This arrangement is what makes benzene so much stable and unique. Now moving on further, it was seen that distance between all carbon atom in the ring was same. So it is very important to remember, since the type of bonding is same, so they all are forming sigma bonds with their neighboring carbon, and they all are doing the sidewise overlap with both the carbon present on the either side. That will result in the same bond length, that means the same distance between the two carbon atom in a benzene ring. Next, it also gives unusual stability because the electrons are delocalized over a large plane, and this extra stability is called as aromatic stability and is a result of unique bonding structure. Next is the CC bond length, as I said, was identical. It was intermediate between the double and single bond, means it was it was shorter than the single bond and longer than the double bond, which is 139 picometer. So you can see here the double bond is 134, the single bond is 154, and your 139 is middle of both of them. And this is the reason they don't go addition reaction. Rather than that, they go substitution reaction. Now, substitution reaction preserve its stability from aromaticity, which is lost in addition reaction. So if you add addition product onto it, it will result in breaking of pi bond and hence destabilizing the benzene. So let's summarize our today's class. So we started with the aromatic compound, which are cyclic, planar, and have delocalized pi electrons. Next, almost all of the aromatic compound that you will study in the upcoming classes will be containing a benzene ring, which is C6H6, and they have a pleasant smell. After that, we have a classification of the aromatic compound as benzenoid containing benzene ring and non-benzenoid containing containing no ring, no benzene ring. Okay. Then we have benzene derivative further. So benzene derivative can be of three types: monosubstituted containing one substituent, disubstituted containing two substituents, and polysubstituted containing more than two substituents. Moving on further, we talked about the benzene structure. So all carbons are sp2 hybridized. It means they are having hybrid orbital, which is the combination of one s and two p orbitals. Further, all the carbon-carbon bond length between the two carbon in a ring were same, and they have a delocalized pi electron system. This delocalization was represented by circle in hexagon. You can see in the back structure that you have seen right now. Further, they have stability features of benzene, which was already due to the continuous pi electron cloud. And this was explained well by the resonance structure, where your double and single bond were moving or resonating across the ring, creating a electron ray. Further, this gives high stability because your electron is being delocalized over a large plane. Now, they prefer substitution reaction rather than addition reaction due to the extra stability of your benzene ring. This was all for today's class. Thank you for your attention.